Good afternoon, everyone. Today, I'm excited to present our work titled Design of Transformer Theft Prevention System Utilizing an Integrated Sensor Network and Real-Time Alerting. This project addresses a critical issue in power distribution industry, transformer theft, which leads to power outage, economic losses, and increased maintenance costs. My name is Mohammad Shifat Hussain, and along with my co-authors, Afsan Amini Chowdhury and Mohammad Firdaus Owaid. We are from Haji Muhammad Science and Technology University. In this presentation, I will walk you through our approach to developing an integrated and intelligent system designed to reduce transformer theft using modern sensor networks and real-time alerting. To give you a clear overview of what we will cover today, this presentation is divided into four main sections: introduction, materials and method, result and discussion, and conclusion and future work. I will elaborate these sections in the later slides. Let's start with the introduction. Transformer theft is a growing issue in many regions, particularly in remote and rural areas, where transformers are often left unmonitored. The theft of these vital components not only leads to the frequent power outage, but also results in significant economic losses and compromises energy security. Our proposed system aims to address these challenges by utilizing an integrated sensor network that provides real-time monitoring and alerting. The system is designed to detect unauthorized activities such as tampering or theft and immediately notify authorities to take action. By preventing such thefts, we aim to reduce safety hazard, minimize the impact on rural communities, and protect the infrastructure of our power grid. Let's talk about the specific objectives of our system. Our primary goal was to design a cost-effective sensor network that can detect transformer theft or tampering in real time. The system needed to be reliable and capable of sending immediate alerts through a communication network. To achieve this, we focus on these following key objectives. Design a sensor network where we incorporate the various sensors to detect different types of tampering, such as wire cuts or physical movement. In real time, in implementing real-time alerts, we ensure that alerts are sent via SMS or calls to authorities immediately upon detecting unusual activity. Optimization of cost effectiveness. We wanted the system to be affordable for deployment in large areas, particularly in rural settings. Ensure reliable detection, minimizing false alarm by using threshold-based decision making. Develop a prototype. Finally, we aim to build a fully functional prototype, test and validate our approach in real world conditions. And these objectives have shaped the design and implementation of our system, which I will explain in the next slides. In the materials and method, I will outline the materials. I will outline the materials and method used for developing the transformer theft prevention system. We used several key components for this system. First, the microcontroller Arduino Mega, which serves as the brain of our system, was essential for processing data and managing sensor inputs. We employed various sensors such as accelerometer, pressure sensor, and proximity sensor to detect unusual, unauthorized movement or tampering with the transformer. The communication backbone of our system is the GSM module, which allows the system to send real-time alerts to authorized personnel when an anomaly is detected. Additionally, we used a buzzer as an alarm mechanism to provide the local alert in case of breach. The method we followed for implementing this system starts with the integrating with the sensor with the microcontroller and configuring them to monitor a specific parameter. We program the microcontroller to process the sensor data and trigger alerts when the predefined it meets the predefined conditions such as transformer motion detection or proximity changes are met. And the system also includes maintenance mode controlled via defined SMS commands to avoid false alarm during a routine checkup. Overall, this combination of hardware components and methods allow us to achieve real-time and remotely monitored security system that protects transformer from theft. Let's now take a closer look at how the system operates. The workflow of the system follows these steps, capture sensor readings. The system continuously monitors the sensor for any changes or unusual activity such as wirecuts, movement, or proximity triggering. Check for changes for the sensors. So if any changes of any sensor detected, the system calculates a cumulative value based on the reading from the defined sensor. Along threshold, the system designed to with a threshold-based approach. It sends the notification also once the alarm is triggered. The system sends the real-time alerts via SMS and phone calls to predefined contacts. For the predefined feedback, it ensures that the system to always be operational. It also sends periodic status updates to the authorities, letting them know the system is functioning properly. This comprehensive or flow ensures the both real-time responsiveness and system reliability in preventing transformer theft. In the subsystem, or you can say our main system is divided into four subsystems: sensor value threshold calculation, alerting system, maintenance and periodic feedback, and power management. Uh, and the next slide, we will see them elaborately. Let's dive deeper into how we calculate sensor values to manage the alert system. Each sensor in the system is assigned at a specific value. For the wirecut sensor, it has a value of 1. We assign them. This detects if any wire is connected to the transformer has been tampered with or not. For the accelerometer, it is assigned with the value of 2. It monitors any movement of physical disturbance of the transformer. The pressure sensor we used a force sensitive resistor. This sensor also has a value of 1 and detects if any port securing the transformer are being illusion or not. For the proximity sensor, we assigned a value of 2. It detects if someone is too close or wanted to move the transformer or the control box. The system only triggers when the cumulative value reaches to 3 or more. This threshold-based approach helps to reduce false alarm caused by minor disturbance or environment factor. For example, a combination of wire cut feedback and proximity sensor triggers would add up to 3, causing the system to activate the alarm and send notification. This method of calculating sensor value allows us to strike a balance between sensitive detection and avoiding unnecessary alerts. And in this slide, I will cover how the system handles maintenance, feedback, feedback, and the power management. For the power management, the system runs on the mainly electricity, but in case of power outage, it automatically switches to a backup battery with a battery management system (BMS). This ensures that the system remains operational when even during power outage, which is crucial for transformer located in remote rural areas. In maintenance mode, in maintenance mode for authorized personnel, the system can be placed in maintenance mode. We have predefined SMS command. This feature allows maintenance staff authorized staff to temporarily disable the alarm system while performing the routine inspection or any repair. Once maintenance is complete, the system can be reactivated by sending another alarm SMS command. And periodic feedback system. It's to ensure continuous monitoring and operation. The system sends periodic status update to the authorities through SMS. This update system inform them whether the system is functioning properly or not, providing a peace of mind that the anti-cheat measures are in place and active. This features backup power, remote maintenance control, and regular feedback are designed to ensure the system reliability and ease of use in real world conditions. Let's look at the result and discussion. We successfully implemented and tested the transformer theft prevention system in a controlled environment. The results are as follows. Threshold-based decision making. Our system uses a threshold. Our system uses a threshold-based approach to reduce false alarm by assigning the defined sensor value and triggering alarm only when the cumulative value reaches 3 or more. The system is both sensitive to real threats and resilient against minor disturbances such as environment changes. And real-time alerts when the tampering is detected, and the system immediately sends alerts via SMS or phone calls to predefined contacts. This ensures that authorities are notified promptly and can take action before the theft occurs. And periodic updates, the system provides regular updates on its operational status via SMS, letting authorities know it's still functioning correctly. This increases the overall reliability and trust for the system. During testing, we found the system effectively detects all simulated theft attempts, and the backup power system ensures the continuous operation even in power outage. And in this slide, I will add a little bit more clarification about how we try to avoid false alarm for our system. Here is just in this slide, there is an algorithm you can see and the format that always checks if any sensor is detected, any changes in its reading to compare it to meet the triggered mode and store its defined value in a variable to be calculated as cumulative value. This variable keeps the track of the total cumulative value as it is used as a system status to be sent periodic feedback also. We'll see the feedback SMS format in the next slide. And after meeting the alert condition, the system activates the buzzer. The authorized members include official staff, the local representative, and whose phone number are predefined in the program to prevent false authorization. And in the right section, we can see a call notification alert in figure 5. In the next slide, in this slide, I will explain the feedback mechanism and how the system provides real-time updates about its operational status. As shown in the example, there is a snapshot of the code, and on the right side there is the feedback message format. And in the format, we can see that the SMS feedback is like this: the device working properly, device mode false, device mode false, and this means it's the feedback from the accelerometer sensor, and the device is mode. The pressure changed false. That means the force sensitive resistor attached in the transformer bolts are not halogen, and it is false. Proximity change false. That means the transformer is not moved anywhere. And worker true. It's a simulated to a test during the result section, and that if any wire is tampered with or not. From the example, we can see that if any tempering occurs, such as wire cut, the corresponding value changes to true, and the system immediately triggers the alarm and sends alert. This periodic feedback also ensures that if any component of the system fails or it is tampered with, authorities will be informed promptly. This feedback mechanism is crucial for ensuring the continuous monitoring. Authorities receive this type of message at a predefined interval once a day or twice a day, providing a real-time snapshot of the system's status. We'll focus on in this slide. We'll focus on the SMS command functionality and how the system controlled remotely through the SMS commands. As shown in the table on the left side, there are three main SMS commands. The command maintenance on disables the alert during routine maintenance and sends a confirmation message as a action mode set to false, ensuring the unnecessary alarms are triggered during the maintenance period. And once the maintenance is complete, the maintenance off command re-enables the alert and confirmation gives a confirmation message as a action mode it's set to true, bringing the system back into active monitoring state. And the third command false the command stop false alarm is to stop any false alarm that may occur, turning off the buzzer and sending a message confirming the false alarm stop. On the right side, you can see the examples how these commands are implemented. We are numbered, labeled as a number. The system response is a command with a corresponding feedback message, providing real-time feedback and ensuring the user is always informed that the system is systems working or systems status. These commands provide flexibility in managing the system to reduce potential disturbance during maintenance and while ensuring the integrity of the monitoring system. And in the conclusion of future work, we can conclude that our work enhances the security and reliability of electricity grid by addressing the transformer vulnerable to theft. In our future work, we plan to integrate GPS system for tracking the lost transformer and at every transformer box as a unique identifier number for precise location in remote areas. Thank you.